So say here's your mean, okay? And remember that your standard deviation is generally some kind of a positive number. It's a distance. So if you go out, if you take that mean, add one standard deviation, so now you're up here. Take the mean and subtract one standard deviation, now you're down here. So between these two numbers, you're going to have about 68% of your data according to the empirical rule. So it's an application that allows you to track where your data is. Does that make sense? You guys with me? Okay. Once we actually use it, it's actually even easier. So we also know that then 95% of the data will be within 2 standard deviations of the mean, and then a whopping 99.7? 99.7% of the data will be within 3 standard deviations of the mean. Okay, so if you have symmetric data, what's the chances that your data value is more than 3 standard deviations away from the mean? Yeah, it's teeny weeny, right? So that's a really good thing for us to know. Oh, Joey, yes, you rock. Thanks. Okay, so that's a really good thing for us to know. You've got symmetric data, which is really, really super, super common. Okay? And if you go 3 standard deviations away from your mean, it's going to be really unusual to find a value that's further away than that. Okay? Further away than 3 standard deviations, right. So let's try an example problem here. You can count on this being on a test. You can put money on it. Okay, either the empirical rule or our next rule, Chebyshev theorem. But these are really widely used. They're really common uses of standard deviation. All right. Yeah. Okay, so here's a problem on page 144 about the empirical rule. It says one measure of intelligence is the IQ test. Okay? IQ scores, among, many, many, many other things, have a bell-shaped or symmetric distribution with a mean of 100 and a standard deviation of 15. So if you've got an IQ of 100, you've got an average intelligence. Okay? So now, we've got our variable is an IQ score. And we know that X has a, what does it say? Bell-shaped, or what is it? Yeah. Bell-shaped distribution. Okay, so right there the empirical rule applies, all right? The IQ scores have a mean of 100, a standard deviation of 15. So if we take that 100, we add 15, and we subtract 15, so this would be 115, this would be 85. Okay, how many people have IQs between 85 and 115? Apply the empirical rule, and it says within 1 standard deviation, 68%. So 68% of people, give or take a couple, have IQ scores between 85 and 115. Does that make sense? You guys with me? Okay? So then if you take
so standard deviation number 2 would be 100 minus 30.
Exactly, Mark, exactly. So now take your mean, add another standard deviation. So now how many people have IQs between 70 and 130? 95%. You with me? And so if we subtract another standard deviation, where are we? 70 minus 15, 55? How many people have an IQ between 55 and 145? 99.7%. So almost everybody has IQs between 55 and 145. Very, very small percentage outside of that. That's where you get those cutoffs that are, people who are, extraordinarily intelligent and people who are extraordinarily challenged on the other side. Okay, so we answered that, we answered that. So how many people have IQs greater than 130? Tell me that. So let's say we've got that symmetric distribution. Okay, it looks something like that. There's your mean right in the middle. Okay? And we know, we've already discussed that 95% of people have IQs between 70 and 130. So let's say, here we are, 2 standard deviations away. You with me? Okay? And we know that between this number and this number are how many? 95%? So what the question is asking is now, what percentage are out there? When you have a symmetric distribution, how does that area, how is it similar or different from this area?
It's symmetrical.
It's symmetric, so it's
2.5%.
it's exactly the same, right? So if you've got 95% between here and here, how much left over? 5%, right? Right, and so you've got half of that 5% on each side. So what percentage of people have IQs greater than 130? 2.5%. Good, good, good. Does this make sense? So you don't have to reinvent the rule, you just use it. You just use it. And you can use it in either direction. You can have the numbers and get the percentage, or you can have the percentage and then go backwards and find the numbers. Let me try to find another problem here. Okay. Let's do the kidney problem. It's kind of disgusting. Hey guys, did you know an adult male? Oh, you got to be between 40 and 49. I don't think that applies to any of you guys. A pair of kidneys in adult males between the ages of 40 and 49 have a bell-shaped distribution, symmetric, with a mean of 325 grams and a standard deviation of 30 grams. So this is probably good information for health professionals, right? Doctors, and if your kidneys are too large to be healthy or too small to be healthy for whatever reason, right? So that's good stuff. So, okay, so 95% of kidney pairs will be between what weights? So what do? We go backwards with the rule, right? So you've got 95%, so we know that's plus minus how many standard deviations?
2.
2. So take the mean, which is 325 grams, subtract 2 standard deviations, and then add 2 standard deviations, and what are those numbers? You with me? You guys with me? Cool. So 95% of these kidney weights will be between, what's the lower? 265 and 385, correct? Grams. Do you guys agree? Is that what everyone else got? Talk to me. Do this or this or this or. Okay, so how do we get 265?
Subtract deviation.
Yeah, so you're going to take the mean. You're going to take the mean and subtract 2 standard deviations. So you've got it's 365 minus 2 times 30. Does that make sense? Yeah.
Mean 325.
325? Oh, yeah, you're right. Thank you. And then to get the 385, you're going to take the mean plus 2 standard deviations, which is 325 plus 2 times 30. Okay, does that make sense? You don't, these rules don't work if you go like 1 standard deviation one way and 2 the other way. They're always symmetric intervals about the mean. Okay? No funky, crazy stuff going on. Yeah, Lauren?
How do you know we have to add it by 2?
Okay, what about the problem? Do we know we had to add and subtract 2 standard deviations? What
95%?
The 95%, yes, exactly. So the rule said that 95% of the data is between 2 standard deviations of the mean.
So is it
2 standard deviations of the mean. And that tells you how many standard, now remember the 2 isn't the value of the standard deviation, it tells you how many you need to add and subtract to get those bounds.
So
Yeah.
is it always going to state whether it's 68, 95, or 99?
Yeah, it'll always be in those,
Okay.
yeah.
You have to determine that, right?
It'll always be either 1, 2, or 3 standard deviations when we're using the empirical rule. We're not going to get real funky. We're actually going to, we're going to come back to this distribution in chapter 7. The symmetric distribution, we'll be doing a lot more work with it. But right now, we're just 1, 2, 3 standard deviations. Yes, Scott?
The times 30, that's always going to be like the given information of the problem,
Yeah.
right?
Yeah, you have to have the value of the mean and the standard deviation. Yeah. Okay, you guys cool with this? Does this make sense? Okay, how about part B? What percentage of kidney pairs weigh between 235 and 415 grams? How are you going to figure that out?
Figure out the standard deviation.
Okay, so do we know the standard deviation?
So this is 3, you know, just look at it, because 265 minus another standard deviation is 235.
Okay,
And the other
okay.
way, so it's 99.7.
Okay, so what we're going to do, what you want to do is take the mean of 325, start adding 30. How many 30s do you add to get to 415?
3.
3. How many 30s do you subtract from 325 to get the 235? 3. So you're within 3 standard deviations of the mean. How much data there? 99.7%. You guys with me? Okay? Anybody confused? Okay. Please ask if you are. Okay, so what percentage of kidney pairs weigh between, let's do part D. Oh. How about part C? This is interesting. So, how many kidney pairs weigh less than 235 or more than 415? So between 235 and 415 on part B, what do we get? 99.7%.
0.3.
So yeah, so 0.3% would be less or greater, less than 235 or greater than 415. You with me? Does that make sense? Take 100%, subtract 99.7%. Okay? Okay. What percentage is between 295 and 385?
68%.
Sorry?
3.15?
0.15. So we've got what percentage between 295 and 385? So take the mean, 325, and start subtracting 30. How many 30s do you subtract to get to 295? 1? Just 1? Okay. How many do you add to get 385? Just 1? So you've taken the mean, you've subtracted 30, and you've added 30 just once to get those bounds. How much of the data is within 1 standard deviation?
So you have to do, it's 2 Ds.
Is it 2 Ds?
Yeah, on the second one. It wouldn't be.
Wait a minute.